And the sheer scale of the super heavy booster is a defiance of traditional aerospace intuition. Standing 71 meters tall and packed with 3,400 tons of cryogenic propellant, it is the most massive mobile structure ever built. But its true complexity lies at its base, a concentrated cluster of 33 Raptor 3 engines arranged in a series of concentric rings. If a single Raptor is a high-performance workstation, the super heavy baseplate is a high-density server rack. For the computer scientist, this is the transition from optimizing a single thread to managing a massively parallel distributed system. And to lift 5,000 tons off a launch pad, SpaceX does not rely on one giant, temperamental engine. They rely on a swarm of smaller, highly efficient nodes. This shift represents a fundamental move away from the mainframe philosophy of the Saturn V's F1 engines toward a cloud computing architecture of propulsion. However, with this parallelism comes a geometric increase in the surface area for potential failure. Managing 33 independent combustion events, each occurring at pressures exceeding 300 bar, requires a level of orchestration that pushes the boundaries of real-time control theory. In the massively parallel propulsion cluster, in a distributed computing environment, horizontal scaling involves adding more nodes to a cluster to handle a larger workload. The super heavy booster is the physical manifestation of horizontal scaling. By using 33 identical engines, SpaceX achieves a total sea-level thrust of approximately 7,500 metric tons, more than double that of the Saturn V. And from a systems engineering perspective, this design offers a significant advantage: redundancy. In the legacy era, the failure of a single primary engine often meant the loss of the mission. In the Raptor stack, the booster is designed with engine-out capability. This is the hardware equivalent of a load balancer in a web cluster. If a single node or engine fails or reports a health score below the safety threshold, the flight computer can gracefully failover by shutting down that engine and redistributing the workload, which is the thrust requirements, to the remaining 32 engines. And the flight software calculates the missing vector in microseconds. It might increase the throttle on the engines diametrically opposite the failure to maintain symmetry, or it might extend the burn time of the entire cluster to compensate for the lost delta V. This fault-tolerant architecture ensures that the mission survives even if the hardware does not perform perfectly. The booster does not need every engine to be a hero. It needs the collective output to meet the mission's service-level agreement. And the choreography of the startup sequence, the most critical moment for any distributed system, is the cold boot. For Super Heavy, this is the ignition sequence. Igniting 33 Raptor engines is not a simultaneous event, but a meticulously choreographed staggered start. And if all 33 engines were to ignite at the exact same millisecond, the resulting overpressure wave, a massive data spike in the atmosphere, could reflect off the launch mount and shatter the booster's own skirt or delicate avionics. To prevent this system crash, the flight computer executes a sequence of staggered ignitions. The inner ring of 3 engines fires first, followed by the middle ring of 10, and finally the outer ring of 20. And this sequence is timed with microsecond precision. Each engine must reach a stable state, where the pre-burners are lit and pressures are nominal, before the next group is commanded to ignite. This is analogous to a rolling update in software deployment, where you ensure the new version is healthy before taking the next set of nodes offline or online. If the heartbeat of any engine fails during this startup sequence, the entire cluster can be shut down before the hold-down clamps are released, preventing a catastrophic failure on the pad. In the acoustic environment, managing mechanical noise, the sheer physical violence of 33 Raptors firing in unison creates an acoustic environment that is almost beyond comprehension. We are talking about sound pressure levels that can liquefy soil and vibrate steel until it behaves like glass. In a cluster this dense, each engine is not just a source of thrust, it is a source of interference for its neighbors. And in previous iterations of the Raptor, the spaghetti of external sensors, wires, and plumbing acted like a series of tiny tuning forks. Each external pipe had its own resonant frequency. Under the massive acoustic load of 33 engines, these components would vibrate sympathetically, leading to harmonic resonance that could snap a sensor line or shake a connector loose. This is the mechanical version of signal noise in a high-speed data bus. In the Raptor 3 monolithic clean design, where the sensors and fluid channels are integrated directly into the 3D printed metal body, is a direct response to this noisy environment. By eliminating external plumbing, as discussed in Chapter 7.3, SpaceX has effectively shielded the engine's nervous system. The Raptor 3 is hardened against the acoustic output of its peers. It can sit in the middle of a 33-unit server rack and maintain its data integrity because there are no loose wires to vibrate and no external tubes to fatigue. In the Roman phalanx, stability through collective action. To visualize how 33 engines keep a 230-foot-tall cylinder balanced on a needle of fire, consider the Roman phalanx. In this ancient military formation, individual strength was secondary to the collective shield wall. If one soldier stumbled, the soldiers to his left and right leaned in to close the gap. And the Super Heavy booster uses its 13 center engines for gimbaling, or thrust vector control. These engines can tilt several degrees in any direction, acting as the rudders of the rocket. The outer 20 engines are fixed in place, providing the raw compute power or thrust, while the inner 13 provide the logic or steering. And this creates a high-fidelity feedback loop. As the rocket ascends, it encounters high-altitude winds that attempt to tip the stack. The flight computer, acting as the orchestrator, sends millisecond-level gimbal commands to the inner cluster. This is a real-time control loop, referencing Chapter 3.4 at an unprecedented scale. The software isn't just managing the throttle of one engine. It is managing the interference patterns of 33 separate plumes. And if the plumes interact in a way that creates a low-pressure zone under the booster, the rocket could be sucked toward the ground or tilted off course. The orchestration software must account for the fluid dynamics of the entire cluster, acting as a single, massive manifold. The 33 plumes eventually merge into one giant super plume, and the software treats this merged exhaust as a single vector that it must manipulate to keep the system stable. In thermal management, in a high-density cluster. In a data center, the biggest challenge is thermal throttling. When you pack too many CPUs into a small space, the heat from one chip bleeds into the next. The base of the Super Heavy booster faces a similar, albeit more extreme, thermal cross-talk issue. In each Raptor 3 is a white-hot furnace. When 33 of them are packed together, the radiative heat transfer is immense. The engines in the center of the cluster are effectively insulated by the engines on the perimeter. They have no heat sink to dump their ambient radiation into. And to solve this, SpaceX utilizes the regenerative cooling loops of the Raptor 3, detailed in Chapter 5.2, not just to cool the individual engine, but to act as a collective heat exchange network. The cryogenic liquid oxygen and methane flowing through the engine jackets act as the coolant for the entire baseplate. Additionally, the monolithic shielding of the Raptor 3, the way the outer shell is designed to be its own heat shield, allows the engines to stand shoulder to shoulder without melting their neighbors. This is high-density packaging at its most lethal. In the log analysis of a 33-node cluster, after a super heavy flight, the volume of data generated is staggering. Each of the 33 Raptors has been streaming thousands of sensor readings per second. This is where the digital twin and predictive maintenance models discussed in the previous section are put to the ultimate test. And SpaceX ground systems perform a multi-node log correlation. They don't just look at why engine number 7 had a temperature spike. They look at whether that spike correlated with a vibration in engine number 8 or a pressure drop in the common propellant manifold. This is distributed tracing for hardware. And by analyzing the diff between all 33 engines, engineers can identify systemic issues that might not be visible in a single engine test stand. For example, they might find that the outer ring of engines experiences 5% more cavitation in their turbopumps due to the centrifugal force of the booster's slight rotation. This data is then fed back into the global model, and the firmware for all Raptor engines is updated to compensate for these cluster-level effects. And antifragility in numbers. The transition from a single-engine architecture to a 33-engine cluster is what makes Starship antifragile. In the old model, more parts meant more things could go wrong. In the Raptor 3 model, more engines mean more data, more redundancy, and more opportunities for the system to learn. In every Super Heavy launch is a stress test that provides a massive dataset for the Raptor's evolution. The choreography of the 33 engines is constantly being optimized. We are moving toward a future where the launch script is so refined that the failure of 2 to 3 engines is treated as a minor exception, a logged error that the system catches, handles, and continues through without the user, meaning the payload or the crew, ever noticing a dip in performance. And this orchestration is what allows the Super Heavy to function as a truly reusable stage 0 for the Starship system. It is the powerhouse that breaks the chains of Earth's gravity, providing the massive initial throughput required to get the upper stage into the environment where it was truly meant to shine. And while the Super Heavy and its 33 Raptors are designed to fight the thick, punishing atmosphere of Earth, the Raptor's journey is only half over. To reach the Moon and Mars, the engine must adapt to an entirely different set of constraints where the air vanishes. The plumes expand to infinite widths, and efficiency is measured not in raw tons of thrust, but in every precious gram of propellant saved. And this shift from the chaotic, high-pressure environment of the launch pad to the serene, unforgiving vacuum of the cosmos brings us to the specialized evolution of the Raptor architecture. 10.2 vacuum Raptors, efficiency in the void of space.